OK， 我们继续上课。上课应该可以更有趣一点，对不对？那好像我们这个老师跟学生可以互相埋怨一下，就为什么上课这么没趣？我们如何可以让上课更有趣一点？星期三的时候，助教答应我，就是要拿一个实验过来，让各位看怎么把这个空气discharge。所以呢，做得好的话会比比表表。但是呢，我还是很希望你们的参与。所以呢，我刚刚做了几分钟，突然想到，我们其实可以让这个课更有趣一点。通常老师开始想如何让这个课有趣一点的时候呢，有时候而且要学生参与的话呢，你要开始串起来了。你们如果平常上课的时候就参与得很好的话，我就不用花脑筋在这里这个找你麻烦了。我开始在想说，我们的小考其实这个你已经考了一辈子嘛，不需要那么多考小考。我们是不是从下礼拜开始或什么时候开始，就是每次下课之前10分钟呢，我们规定每个人要问至少一个问题，然后当做你们的这个成绩。问问题的能力是非常重要的 ，OK。那当然你可以把老师挂在这个黑板上，答不出来，不过没关系，反正我脸皮也厚。我们其实可以试着想想看，对，这个我们小考就不要考了，然后下课前10分钟到下课后半个小时，我们都可以来让我们同学们问问题，然后你问的问题呢，就变成你这个学习成绩里头最重要的一部分。问问题的能力很重要，非常的重要。这个我最近5、6年跟俄国那里的联系比较多，发现他们的这个教育里头，他们的期末考，尤其大学部的期末考，是用口试的，不是用笔试，因为他们每一班的人数不多，刚好我们这一班的人数不多。口试跟笔试有很大的不一样，笔试通常就是在找一个标准答案，然后呢，你做出那个标准答案，就表示你的能力很好。但是呢，你将来遇到的问题通常没有标准答案。那这个口试其实通常没有标准答案，然后呢，最近我又了解到，这个以色列家庭他们小孩子回家的时候呢，爸爸妈妈问的是你在学校里头问了什么问题，不是你在学校里头学到什么东西。所以somehow这个台湾的教育应该要有一些改进，我们来改改看。所以我来想想看，我想这个下礼拜1开始，我们就可以来试试看，让你们问问题。你问的问题通常是因为你想过，你才会有问题，所以我们试试看 ，do some experiment， 然后呢，看看怎么协助你们，让你们的学习更好，然后呢，对你们自己的这个将来未来的这个准备更好 ，OK。你如果有什么想法的话 ，email 给我，我们看看怎么让你们参与这门课，会很有趣。我们想想看 ，OK，let me continue this part。我通常这些这个想法呢，对一个老师来讲，最担心的其实是这个课会 delay， OK，有些东西在我们教育里头似乎是这一门课到某个时间就要教到什么地方给你，但是你发现呢，其实你已经读书读了一辈子，很重要的能力并不是带着你去读一些东西，很重要的能力的建立是除了你自己有办法自己读之外，就是一些思考的能力，问问题的能力，或者是做 presentation 能力，这些呢是你自己没办法去不容易自己去训练出来的。所以呢，我们试着做看这门课，剩下一半的时间，看我们能够改进到什么程度。OK， 所以 good。你现在有心理准备了哈。All right, want to calculate the electrostatic force. For example, if you have a capacitor like this, and you want to figure out the force between these two plates, well, somehow you have to do some experiment to deduce the force. Okay, and so when you do the experiment, you have to consider your whole system, right? Suppose that you have two parallel plate capacitor like this, but it's also possible that you set up one experiment with a source connected to it, right? So you could have a source in your system, and you may or may not have a source. So let's separate the experiment into two parts. The first part is that you have a source connected to the capacitor, and this is going to be an external power supply. Okay, so you have a power supply connected to it, and later on we'll be talking about a system without a power supply, and then the final answer should be the same. Okay, now in this system you have a change of energies. 这个是能量，所以对我们来讲 when we talk about energy, there's a golden rule. The rule is that the energy has to be conserved. Conservation of energy has to apply. So in this system, you have a source. So any change of the energy in the system got to be related to the energy supplied by the source, right? So think about that when you try to pull apart these two plates, you put in some energy, right? And so you have some mechanical energy you put in. But for this system, well, you have two parts. One is this, one is this. This is the energy supplied by the source. And this is the energy, mechanical energy you put into the system. But this charge system has a stored energy inside. So in fact, the stored energy also change because the change of charge in this system. Well, for this system, you have a constant voltage. Okay, you have a constant voltage. So when you try to pull it or push it, the stored charge in fact change. Okay, and this stored charge, this dWe, in fact is equal to 1/2 V dq. This is a stored energy, right? But if you have several charges in the system, then you have to do a summation over a different part of the charges. Okay, for the source, the change of the energy is going to be equal to V dq, because your voltage is fixed. And then you simply supply charge to this system to compensate the change of the energy due to this mechanical energy and this internal energy. So you have to supply external energy to compensate the change of the energy you put in, and also the change of the internal energy. Okay, from energy conservation， 这是外头的系统放进来的。然后呢，你在这里这是你放的这个 mechanical energy， 然后它本身的这个储存能量的改变了。Okay. And if you have multiple capacitors, then of course you need to do a summation like this. OK， 所以呢，在这里你事实上你发现这个东西呢是有2倍的差别 ，a factor of 2 difference. So you can write like a dWe is equal to dWm, and this dWm is equal to F dot dL. This is a mechanical energy you put in. Okay. And 这个你以前学过 dWe dL is equal to gradient of WE dot AL. Right. 这个是你以前学过，在学这个 gradient 的时候的一个式子。So your F right here is equal to gradient of WE, the gradient of the internal energy. So you end up having this expression. And but for this experiment, we fix the voltage right here. So we better to label this is V equal to constant. Okay, V equal to constant. 有没有问题？好，我们来实际算一下。Based on this, V equal to constant. This WE, V equal to constant, is equal to 1/2 CV squared. We just have it on the last page. And this C is equal to epsilon for parallel per capacitor. This is going to be epsilon S divided by, now this dl, you want to pull it. So dl is a variable. So let's put y. Suppose that this direction is y. Okay. The separation of these two parallel plates is going to be a variable right here, y. Okay, and then v squared. Now we can calculate the force. Okay, just take gradient of this. So you have gradient of WE. That is gradient of 1/2 epsilon S y v squared. 这里头的变数，唯一的变数是这 y. So this become 1/2 epsilon S. And then finally y will settle equal to d. Okay, just change a little bit of y. So this will be y squared minus 1. And then v squared dy, and this is along y direction. Right? You just do a gradient to y. You end up having minus sign here because you have y on downstairs. 那这个呢，有 y is equal to d. So this gives you 1/2 gradient of v. So this is事实上这个是 y 的微分下来了，没有这个了。Okay, you do a gradient differentiation. F equal to gradient. Okay, 所以 y 掉下来之后呢，把它写成 d。所以呢 ，you have 1/2 c over d v square 用 y direction。OK， 所以这个是你如果有一个 constant source 在那里的话you end up having this expression。OK， 那等一下 we have another one example. Am I doing right? 这是 c divided by d v square ay. So this is your force. Oh, minus sign here. We have a force like this. OK， 那所以这表示呢，你要把它 if you want to pull it apart, there's a minus y force to pull your hand back to the along the minus y direction. Okay, so this is how you do it. The calculation for the force with a constant v connected to a capacitor. Now let's do a second experiment. Suppose that this experiment is not connected to an external force. So originally you have positive Q here, negative Q here, and you have a separation of D. Okay. For this system, now we write down the energy conservation. For this system, you don't have external source. So your energy conservation basically is this. Okay, and this is associated with a constant Q because you don't connect it to an external source. So you don't. It's not related to the voltage. It's not. There's no constant voltage between these two plates. But when you pull this apart or push it, the voltage across this is going to be changed. 它的电荷不变，但是你拿开或压下去的话，这里的电压会改变。Okay, so you still have this equal to like a summation of QK dV. Okay, and this is equal to your force multiplied with dl. Okay, so you end up having this F dot dl equal to minus dwe with a constant Q. OK， 没有问题 ，right？ 所以呢，你得到一个结果，在这个实验里头 ，this force is going to be equal to minus gradient of we with a constant Q. Now, we can do a calculation for this case to derive the force. Basically, your internal energy now, previously you have 1/2 CV squared with constant V. Now you have to convert this. You have to convert this into, based on C, V equal to Q over C. So you can convert this into 1/2 Q squared over C. This C, again, we have an expression of C over there. 所以呢，你的 C is equal to epsilon s divided by y you put this into this expression to get WE equal to 1/2 Q with a constant Q, 1/2 Q squared, and then Y epsilon S. Now, you can do F equal to minus gradient of WE as with a constant Q, you can do this calculation. 这个计算容易多了 right? Minus gradient of WE as a function, for a constant Q is going to be equal to 1/2 Q squared, 1 over epsilon S. Okay. Minus sign, so you need to put a minus sign here. And then this is along minus AY direction. 这个是你的 force. If you compare this with this, 它们的答案是一样的。你如果把 C 写成 Q over V 的话，这两个式子会是一模一样。Okay. A simple conversion. 方向也没有错，都有负号在那个地方。Okay. So this is how you do so-called thought experiments. How you do thought experiment to derive the force in the charge system. Okay. If you have an external source with a constant voltage, then the force is going to be equal to the gradient of the internal energy fixed at some constant voltage from a power supply. And if you have a system that is not connected to a power supply, this is disconnected, then you have fixed charge. Then based on this energy conservation, I just took it out. Then you have a result. The force is going to be equal to the gradient of the stored energy with a minus sign in front of it. Okay. 那在讲解这个公式的过程里头，我很清楚的把它做个计算给你看。Okay, for fixed voltage and for fixed charge, you end up having the same expression here and here. Okay. 你可以很快的做一个这个 verification， 一模一样答案。Okay, and this is in fact one of the examples in your textbook. Okay, so this is a force associated with the charge system. Any question? 有没有问题？没有的话呢，我们要进入下一章。Well, we have several ways of calculating the electric field and electric potential. And this chapter is going to give you another scheme, another approach to solve the electric field and electric potential. So in the last chapter, we have two ways to calculate the electric field and electric potential. Number one is Gauss law. Right? If you have enough symmetry, then you can deduce this D as a function of some charge. And then from this D, you can calculate electric field. Okay, this is Gauss law. And number 2, you can do distributed integration to derive the electric field and electric potential. In particular, you have V is equal to 4 pi epsilon R rho d. Some variable could be V or surface or length. If you have a charge distribution over some space, right? It can be a line charge, it can be a volume charge, it can be a surface charge. 所以这里呢，有可能是这个line surface volume, line surface volume. And then you can calculate electric field as gradient of V. Okay, and don't forget the minus sign right here. 那但是呢，你如果数学上看这个两个 postulate 的话，you have curl of equal to 0, then it gives you electric field equal to this minus gradient of V, electric potential, and the other one is divergence of D equal to rho. In fact, you can combine these two together to get this so-called Poisson's equation. Okay. This is more like a mechanical, this is more like directly working on the postulate of the electrostatics. And then this is more like a mechanical, geometrical way to deduce the voltage and electric potential. But this is more like a mathematical approach to figure out what V is given this expression. Okay. But sometimes your charge is here. 你的电荷可能在这里 but you want to figure out V somewhere here, far away from the charge. 当你看到这个式子的时候呢，你在看的是一个 point, 一个 point function. It's telling you a point in space. Okay, at this point, there's charge associated with it. But sometimes you have some potential, electric potential somewhere where this location is far away from this charge. Okay, so you have Laplace equation by taking out this charge. You end up having this expression. So this chapter is going to deal with the solution of these two equations from mathematical point of view. 那这是 differential equation, so you know that you need to have boundary conditions to give you a unique solution to these two expressions. Okay, 所以呢，除了这个第一个方法之外 this is the Gauss law and this is the distributed integration. And then now we're looking for solutions to Poisson's equation and Laplace equation, subject to some boundary conditions. Okay, so this is the purpose of this chapter. Now, before you look for solutions of Poisson's equation and Laplace equation, of course you need to be familiar with the Laplacian operator in the 3-coordinate system. 所以这是 x, y, z coordinate system 里头的这个 Laplacian operator 给你的一个形式。那在这个 cylindrical coordinate 跟 spherical coordinate, you can always check a table to find out these two formulas. OK, 好，我们先给一个这个 general description, right? 你从这里找到你的 electric potential 之后 well, then you can do minus gradient of electric potential to get electric field. Okay, and if you are interested in the charge density, surface charge density, then you get the normal component of electric field. Basically, normal component of displacement vector D to get your charge density. So let's go back to the simplest problem we have. 以前最简单的一个是这个图形，就是这个parallel plate capacitor. 我们来解一下，就是它里头的这个 electric potential 是怎么样的，应该是怎么样？从这个Laplace equation, because in this region, you are interested in the electric potential, electric field in this region, where you don't have isolated charges. 你的 isolated charge 在这里跟在这里。Okay, so let's just bring up the Laplacian operator, right? And put this into a Laplacian equation equal to 0. So you end up having this. But because of this geometry, assume that this electrode is very, very big, okay? And you only have variation along y direction. So you don't need to deal with this. You don't need to deal with this. You only have this equation. And from this ordinary differential equation, you don't have variation along x and z, so this becomes an ordinary differential equation. And you have a solution of this kind with unknown constant C1 and C2. 那你知道标准的解这个 differential equation 的话，基本上就是把这个边界条件带进来，你就可以解得出来。OK， 这个边界条件是什么呢？ At y equal to 0, this is grounded. At y equal to d, you have a voltage V0. So you have two boundary conditions that will allow you to solve for two unknown variables. 两个式子解两个未知数 ，right？ 所以把这个边界条件带进来之后，你就得到这个 C1， 这个 C2 has to be equal to 0, right? And C1 has to be equal to a ratio of V0 divided by D. So you have a V solved from this Laplace equation given by this. 非常简单的一个例子，没问题 ，right? Okay, now the second step is to find out the electric field by taking minus gradient of V. This gradient operator gives you a differentiation of y with respect to y. So very straightforward. You end up having an electric field along minus y direction. 那这个其实就是你之前已经得到的这个计算 ，OK。然后呢，这时候呢，你可以去算它的 surface charge density. Alright, because you know the E, the normal component of electric field, so you can find the surface charge density from this boundary condition. Alright, D, but don't forget that you have the dot with D with the AN2. AN2 的话，你要注意到是这个导体出来的这个面的方向 AN2. Alright, so for the upper plate, you have a surface charge density like this, and then lower plate, you have a surface charge density that has a minus sign in front of it. Okay, 电荷的话有正负号 you have to be careful about the calculation. And the key is that you have to identify the direction of your AN2. That is the key. So this very simple example tells you the steps to calculate the electric field and also the charge density subject to a Laplace equation. All right. For this case, it's a Laplace equation. You don't have charge in this region, but sometimes you have to deal with the charge. Then you need to use Poisson's equation. OK， 这是 Poisson's equation. 这个零的话就是 Laplace equation. So this is a very simple example. Of course, we have a little bit more complicated example. And this is also something you already worked out before by using Gauss law. 你之前已经用 Gauss law 算过这个问题了。OK， 我们来看一下。In fact, you can use the Poisson's equation and also Laplace equation to solve this problem. Well, the problem is that you have a charge ball with radius of RO right here, and you want to figure out the electric field and voltage, electric potential everywhere. 所有地方的这个 electric field and electric potential. OK， 那你如果用这个 Poisson's equation and Laplace equation, you have to know the boundary conditions. Okay, so the first step is to figure out the boundary condition for this problem. Well, the boundary condition is that at r equal to 0, you have nothing. So electric field is equal to 0. When r is very, very big, then your electric potential and electric field both approach 0 because just become a point charge, right? At infinity, your electric field and voltage have to go to 0。这是两个边界条件，在 r 等于0跟 r 等于无限大的地方。另外呢，在这个边界上头，真正的边界上头，你的这个 d and v are continuous。什么状况之下 d 不是连续的？什么状况之下 d 不是连续的？它有表面电荷的时候。Okay, this is a volume charge density. There's no isolated surface charge. Therefore, d and v are continuous. V is always continuous because it's work. If you do some work, it has to be continuous. Okay, and v is discontinuous if you have surface charge, and usually it's on the surface of an electrode. 金属的表面 because in a piece of metal you have infinite amount of charges. Therefore, on the surface of a metal you have surface charge, where your d is not continuous. Okay, but v is always continuous. 那这个再下来呢，就是一堆的这个数学的计算，然后呢 match boundary condition. And if you feel confused, you can go back to just follow steps and do it by yourself. All right. So I'll just go through this one time, and hopefully you can catch the concept. Well, within the region where you have the volume charge density, you use Poisson's equation, because now in this region you have volume charge density, so you have to use Poisson's equation. And this is a spherical symmetric system, so you need to use the spherical coordinate system to describe it, right? On the right hand side, it's like this. On the left hand side, now we put the minus sign before this charge density to remove this minus sign. So on the right hand side, you have rho 0 divided by epsilon 0, and in the left hand side, you have the spherical symmetric expression for the Laplacian. 在这里没有 d theta d phi because we assume that it's a uniform charge ball. Okay, and then you move this r squared to the right hand side and do an integration, and then divide the whole thing with r squared. So you end up having this expression. In this expression, we take out this term. Why? Because dv dr is minus e. And we said that this boundary condition r equal to 0, e equal to 0. 如果说这个 r 这一项不拿掉的话呢，这个 r 当趋近于0的时候，这一项变成无限大。It's not acceptable because you're calculating the electric field containing the point where r equal to 0. Okay, so you apply your first boundary condition to remove this term. Okay, 第一个这个边界条件让你把这一项拿掉了。那这些其实就是在算这个 Laplace equation 跟 Poisson's equation 的时候呢，就不断的把这边界条件放进来，然后把这个未知数呢把它找出来 ，right？ And then you have dv over dr, but that your minus gradient of v is that equal to minus dv over dr. So now immediately you have the electric field in this region. And you can verify this expression by using Gauss law. OK， 好，所以在这里头的 electric field 你知道了，那你开始算这个electric field and electric potential outside this charge ball. Outside this charge ball, you don't have any charge, so you have Laplace equation. Just put 0 on the right hand side of your Poisson's equation. Okay, and again, you find the formula for the Laplacian operator. On the right hand side is 0, so you end up having dv dr equal to this. So your electric field is a minus sign of this. So you end up having this expression. Well, in this expression, you have an unknown, that is C2. Again, you need a boundary condition to solve for C2. And so you know that at the boundary, D component, D is continuous because there's no surface charge. OK， 所以呢，之前在上一页 ，you already have electric field inside this region, and now on this page you have electric field outside this charge ball. So at the boundary they have to be continuous. So just equate this expression and the last expression at r equal to b. OK, at r equal to b. 把这个 r 把 b 放进来，这时候呢，你就可以找出 C2 是什么东西了。Okay, well, you simply have to go through this calculation by yourself. Okay, step by step, matching the boundary conditions, write down the Laplacian operator, and in the Laplacian equation, and then match boundary condition, and then you can figure out the electric field. All right. 那这个 v 的话呢，其实当你在算 electric field 的时候，你的 v 已经先算到这个程度了，第一个微分。So you simply have to do one more integration. Once you do one more integration, you pop out a second variable. You pop out another unknown, C3. All right, and the boundary condition require continuation of the v across this boundary. 所以呢，多出一个未知数没问题，你再加一个边界条件进去，你就可以找到这个，它的这个值。那另外呢 ，r 大于 b 的时候呢，你再做一个积分，也会跑出一个未知数出来。但是你知道 ，outside this region, your v has to go to 0 when r approaching infinite. So very quickly, another boundary condition at infinite, remove this C4. Okay, so then you only have one unknown. You match your boundary condition at r equal to r equal to b, then you can figure out C3. Okay, 所以这一连串的计算呢，基本上都是这个代数的问题。You have to do it by yourself. But there's only one trick to do this. You write down the Poisson's equation or Laplace equation, and then match your boundary conditions to find out all the unknown variables. That's it. Figure out all the unknown coefficients. 所以它只有一个基本的步骤，是这样子而已。Okay, so this is the example. 有没有问题？这是直接从 Poisson's equation and Laplace equation 下去解问题，纯数学的这个differential equation， 然后呢 match boundary conditions, you get the answer. Next time we'll be talking about method of images. That is also a technique to match the boundary conditions, cleverly installing some charge somewhere. Okay. So this is not a pure mathematical approach, but you have to sort of cleverly select some locations to put additional charges into the system to match your boundary condition. Okay, so we'll start our discussion from this method of image next time. And before you go, we do have one quiz today.